And welcome back. Okay, first I want to talk through some of the basics, like standing still, and actually show you what it looks like on each graph. And then slowly moving, when they're moving away, moving toward, and look at some of those. Now, first off, up here, if we have a position time graph where we are just standing still, it's just going to be a horizontal line. It's not necessarily going to be at zero, but it's going to be some horizontal line. Now, the velocity from that, if this is a horizontal line, then this has to be a horizontal line at zero. And if this is zero, then this is also zero. So both the acceleration and the velocity are a horizontal line at zero, when this is a horizontal line anywhere. And this is some of the tiering, like T-I-E-R, that we were talking about today in class. Now let's talk about moving away. So in this one, we're moving away from the detector. We are traveling with a constant velocity away from the detector. We can tell that the velocity is constant in this graph because the line is straight. Okay, there's no curve to it. It's straight. It's not horizontal, but it's still straight. So since our velocity is a positive slope, it's sloping up, that means down here that our velocity graph would be a horizontal line above zero. Okay, so this would be the velocity graph that went with this position graph. Now this, we see the same thing that we did over here. Going down a tier, the position is staying the same. It's not changing, so the velocity is zero. If the velocity is staying the same, then the acceleration is going to be zero. So the acceleration is actually zero for this graph. Now, if this was sloped the other way, which I'll grab a different color and do real quick. For this graph, and I'm not sure how well you can tell that that's a different color, but it's supposed to be black. Where is it? Black, and then this one that I just did is blue. Okay, for this one, we have a negative slope because it's sloping down instead of sloping up. Since this has a negative slope, it would be below zero to indicate motion toward the detector. It's still a straight line, though. So since this up here is a straight line, this is going to be a horizontal line. Now, since this is a horizontal line, we have the same thing again. The acceleration graph is going to be a horizontal line at zero, because if the velocity is constant, the acceleration is zero. If the position is constant, the velocity is zero. Okay, now, let's not worry about this one so much, and let's talk about the velocity. Okay, if the velocity is increasing, okay, so we started at rest, and our velocity is increasing. Now, specifically, it is increasing as we move away from the detector. It's away because we are above zero. We have a positive velocity. That means we're moving away. So if this is away from the detector and it's positive slope, the acceleration has to be a horizontal line above zero. So here, this is because it's horizontal. It's horizontal because this is straight, much as this was horizontal because this was straight. Since this is horizontal, the jitter graph for this motion right here, would be zero. The acceleration is constant, so there is no jitter present. The jitter would be 0. I'm not going to graph that because I don't have room and you wouldn't be able to see it anyway. Now let's switch it up. If our velocity is still in the same direction, but now we are slowing down. This time we have a negative slope. Since our slope is negative, that means that our acceleration has to be negative. But our slope is still constant. So since the slope is constant, that means that the acceleration has to be constant. So the acceleration would be a horizontal line and negative, below 0. Now, when we start going backwards, we're looking up here at the position time graph to make the black line. My cap doesn't work. Okay, we started at rest and we moved away with an increasing velocity. So we start at rest, but as we move away, we go faster and faster and faster. Well, we said here that the steepness of this line is the velocity. So if our velocity is increasing, then our slope has to increase its steepness. So it would curve up as time passed. For the other one, we start with a high velocity, still moving away, but we are slowing down. So this one would start steep because we have a high velocity, but we are slowing down as we go, as our velocity approaches 0. So this line would be the position graph of this line. And this line would be the position graph of this line. Now, what if we change the velocity so that now the velocity is negative? Both of these graphs, the blue and the black for all three of these, are assuming motion away from the detector. So what if we change it to toward the detector? So let's say that we are moving toward the detector, but speeding up. So toward the detector speeding up would be this, because our velocity is getting farther and farther from 0. Negative just means toward. So the fact that this is all below 0, all that tells us is the fact that we're moving towards. The fact that it is constantly decreasing, or sorry, not decreasing, but that it's becoming farther and farther from 0, it's becoming more and more negative, tells us that we are actually speeding up. And so this line right here will give us a negative acceleration, because our acceleration is a negative slope. It's sloping down. Okay. While if we go the other way, if we start moving towards, but we're slowing down, that's going to look like this. So in this case, we're moving towards the detector, but we're slowing down as we get there. So we started moving quickly, but the closer we get, the slower we go, until we eventually get to 0. Now, in that case, again, straight line means that we have a horizontal line here, but this has a positive slope. So since our slope is positive, our acceleration would have to be positive. Now, notice, here the blue line had a positive slope, and here the black line had a positive slope. In this one, we are moving away and speeding up. In this one, we are moving towards and slowing down. Both of those motions look exactly the same on the acceleration time graph. As you come down, you get more information about some things, but less information about others. You can no longer tell, by the time you get to acceleration, you can't actually tell what direction you are traveling in. You know the direction of the acceleration. You're accelerating away or you're accelerating towards. You know the direction of your velocity based on whether you're speeding up or slowing down. But just looking at the acceleration graph, just this line, all you know is your acceleration is positive and that your velocity could be increasing, it could be decreasing. You can't tell looking at this. Now, if I told you that your acceleration was positive and your velocity was away, well, that's positive and positive, you could figure out that you're moving away and speeding up. But with just an acceleration graph, you cannot tell me the direction you're traveling in. So keep that in mind as you start thinking about these graphs. Every acceleration graph, every line can represent multiple velocity graphs. Just like this line and this line, they are exactly the same on the acceleration graph. But one represents this line, which is moving towards the detector, while the other represents this line, which is moving away from the detector. That's why we're not going to work much with acceleration graphs. We're mainly going to be focused on the first two, position time, velocity time. What I may ask you to do is interpret what the acceleration time graph would look like based on a velocity graph, and maybe even based on a position graph. Like, for example, this one right here, I'm pointing, there we go. On these, you should be able to tell me that if this is a straight line, the acceleration graph has to be 0. Unless this is curved, unless your position graph line is curved, your acceleration cannot have any magnitude other than 0. Now, to finish this video up, I'm going to go ahead and do these two lines for these two velocities. So we are moving towards the detector with a positive acceleration. Negative velocity, positive acceleration. We are slowing down. Our velocity is becoming less and less and less and less, slowly approaching 0. So we are moving towards the detector, and we start with a relatively high velocity, so a steep line. But as we get closer and closer and closer, our line levels out as we approach 0. This one, also toward, but we're starting pretty close to rest, and we are speeding up as we go. So we start, and we're moving towards fairly slowly, but as we go, we speed up, and we speed up, and we speed up, and the line gets steeper and steeper. I hope that this helps a little bit, especially for those of you who still have that homework, that lab homework, because you forgot to turn it in today. I hope that this helps out, especially since the quiz I am going to post Saturday morning. Okay, the velocity time graph quiz I'm going to post on Saturday morning, and you'll have until midnight Saturday night to finish it. Okay, I hope this helps. Let me know if you need any extra help.